This video is sponsored by Brilliant.
Today we're going to look at an interesting but not very well-known class of functions known as parabolic trig functions. So the motivation here is that in the real plane, there are exactly three classes of quadratically defined curves. And those are going to be parabolas, circles or ellipses, and hyperbolas. So we know circular trigonometry, that's just what we would generally call normal trigonometry. We know the hyperbolic trig functions like hyperbolic sine and hyperbolic cosine. So it stands to reason that there should also be parabolic trig functions. So let's recall a couple of defining properties of the normal circular trig functions and the hyperbolic trig functions and see if we can use those to come up with maybe a reasonable definition for some parabolic trig functions. Okay, so let's start with the circular trig functions. So cosine and sine are generally defined so that they parameterize a unit circle. So here we've got a unit circle x squared plus y squared equals 1. And if you take an angle of t radians from the positive x-axis, then this point right here has coordinate cosine of x or cosine of t, sine of t. And that's a defining property of cosine and sine. But that means that they satisfy the following equation. That's known as the Pythagorean trig identity. So cosine squared plus sine squared is 1. Furthermore, using some other defining properties, you can derive their derivatives, which are well known. So the derivative of sine is cosine. The derivative of cosine is negative sine. Furthermore, well, cosine and sine are solutions to the differential equation f double prime equals negative f, but we could generalize that a little bit by saying that these are generally solutions to a differential equation f double prime of t equals minus a squared times f of t. So I put an a squared here so that we know that that's always positive, so this minus sign makes the thing on the right-hand side negative. And I should say here that a is not equal to 0. So actually the solutions here would be sine of a times t and cosine of a times t. Another way of getting at the trig functions is via the following rule. And that is cosine of t is the unique number satisfying this equation right here. So we've got half cosine times sine plus the integral from, that should be a cosine of t down there, up to 1 of 1 minus u squared in a square root du equals t over 2. That comes from measuring the area of this little sector a couple of different ways. Okay, so now let's move on to the hyperbolic trig functions, and you'll see a lot of parallels here. So the hyperbolic cosine and the hyperbolic sine are methods for parameterizing what I'll maybe call the unit hyperbola, x squared minus y squared equals 1. And so since they can be defined as maybe a parameterization of those, that means they must satisfy hyperbolic cosine squared minus hyperbolic sine squared equals 1. And then via that sort of definition, along with some other properties, you can derive their derivatives. So the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. No need for a negative ever. And then hyperbolic cosine and hyperbolic sine are solutions to the differential equation f double prime equals f. But generally, they're solutions to f double prime equals a positive number times f. So we're writing that as a squared times f, where a is not equal to 0. And then furthermore, we could have the same sort of area definition that we had with cosine that we get from measuring the area of this, maybe I'll call it a sector of the unit hyperbola, two different ways. So here we have half hyperbolic cosine times hyperbolic sine plus the integral from hyperbolic cosine up to 1 of the square root of u squared minus 1 du equals t over 2. Okay, great. And like I mentioned, that uniquely defines the hyperbolic cosine. So let's look at all of these properties of circular trig functions and hyperbolic trig functions, and we'll use all of these properties to explore parabolic trig functions.
If you're looking for a free and easy way to learn more about trigonometry or a number of other subjects in mathematics and science, check out brilliant.org. Are you ready to elevate your intellect and embark on a journey of discovery? Dive into the world of knowledge and ignite your intellect with brilliant.org. Brilliant is an online learning platform that's as engaging as it is effective. Brilliant offers interactive, hands-on courses designed to make you not just understand, but truly master concepts in math, science, computer science, and more. You will be able to complete whole topics gradually in as little as 15 minutes per day and learn anywhere, anytime, on your phone, tablet, or computer. And Brilliant will support you every step of the way. Brilliant makes learning more like a game, with fun features that let you challenge yourself and compete with others. No matter what skill level you're at, Brilliant can help you improve. I'm currently excited about the quantum computing class. It's helping me relive my days as a physics major. Brilliant makes learning dynamic, engaging, and more importantly, effective. Treat yourself this winter to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial, and the first 200 people will get 20% off their annual premium subscription. Thanks once again to Brilliant for sponsoring today's video.
Okay, so let's start with the differential equation motivation. So we know that if we've got f double prime equals a negative number times f, then that gives rise to the normal trig functions. We know that if we have f double prime equals a positive number times f, that gives rise to the hyperbolic trig functions. And so, well, what's missing there? Well, if something's not positive or negative, it must be equal to 0. So that means f double prime equals 0 times f should give rise to parabolic trig functions. Okay, well, so what does that mean? Well, it looks like things are going to be very, very simple are going to end very, very quickly. But you'll see that that is not the case. So if we've got f double prime of t equals 0, that means that we have f double prime equals 0, but that has maybe a pretty simple solution of a linear polynomial. So we've got f of t must be of the form c1 of t plus c2 of t. But that's pretty boring because, well, which part of this is the hyperbolic, or sorry, I should say the parabolic sine, and which part of this is the parabolic cosine? Well, it's a little bit unclear given our goals. So what we need to do is we need to split up this maybe general solution, c1t plus c2, into the parabolic sine part and the parabolic cosine part. So in other words, as a linear combination of the two parabolic functions which we need to get at. Okay, so maybe another way of thinking about sine and hyperbolic sine and cosine and hyperbolic cosine, whereas parameterizations of the unit circle and the unit hyperbola. So perhaps we need something like the unit parabola. So let's introduce that over here. So I'll call this the unit parabola. And I'm not sure if this is like a standard name for this object, but I think for our purposes this is pretty good. And so we'll take the unit parabola to be the curve y squared equals 1 minus x squared. Sorry, not y squared, y equals 1 minus x squared, because, well, we need that to be a parabola. So let's compare with the unit. So let's compare this with the unit circle, which is y squared equals 1 minus x squared. You know, things moved around a little bit. and the unit hyperbola, which is y squared equals x squared minus 1. Well, notice they're kind of similar, but here we've got a y instead of a y squared, but that's necessary because we want a parabola instead of a hyperbola. Okay, so let's get a graph of this on the board. Okay, so that shouldn't be too hard. So let's say there's our xy axis, and here's sort of obviously the point 0, 1. Then we've got a parabola. So here we've got, like I said, 0, 1. Here we have negative 1, 0. Here we're going to have 1, 0. And like I said, this is the graph of the curve, y equals 1 minus x squared. And, well, like I said, our whole goal is for these parabolic functions to parameterize this. So what we should have here is this sort of point right here is of the form parabolic cosine of t, comma, parabolic sine of t. And, well, perhaps it should also satisfy some like standard values that the hyperbolic and the circular functions also satisfy. So perhaps we should have the parabolic cosine of 0 is equal to 1. And then we should have the parabolic sine of 0 is equal to 0. So let's see, that means that this point right here is the point where the parameter is equal to 0 for what it's worth. And then, well, what's the maybe version of the Pythagorean identity here? So I think that's pretty easy to see because these two new functions have to lie on this curve. So we also need this parabolic sine of t plus the parabolic cosine of t squared adding to 1. Now we'd like to use that area definition for the cosine and the hyperbolic cosine to motivate an area definition for the parabolic cosine. So let's get this thing right here. Okay, great. So let's see if we can measure this area two different ways. So I think one way, using the parameterization, you'll get the following formula. So you'll have 1/2, and then you'll have hyperbolic or parabolic cosine times the parabolic sine. And then we've got plus the integral from the parabolic cosine up to 1 of 1 minus u squared du must be equal to t over 2. So let's observe that that looks exactly like what we had for the regular cosine and the hyperbolic cosine. All that's different here is this function that's happening in here, but those depended on whether we were in the circular world, the hyperbolic world, or, well, now the parabolic world. And this equation right here uniquely defines the parabolic cosine. That being said, what we'd really like to get at the moment is the derivative of the parabolic cosine and the derivative of the parabolic sine. Okay, so we can in fact get that simply from differentiating this formula. Okay, but in order to do that, let's do a little bit of prep work first. So maybe let's replace this parabolic sine with, let's see, 1 minus the parabolic cosine, which we can do from the formula that is satisfied. Also, let's multiply both sides by 2 to clear fractions. So let's observe that we now have the following equation. We have parabolic cosine times 1 minus parabolic cosine squared plus 2 times the integral from parabolic cosine up to 1 of 1 minus u squared du equals t. Okay, but now we can multiply out this left-hand side, and we'll end up with parabolic cosine minus parabolic cosine cubed. and then plus all of the rest. Okay, so let's maybe start with that at the top of the next board and see where we go. So our immediate goals are the derivatives of these parabolic trig functions. So we're going to get at this from taking the derivative of this defining equation for the parabolic cosine, which we wrote down on the last board. Okay, so, well, let's take that derivative. So this derivative of parabolic cosine, we'll simply write that as the parabolic cosine prime. And then here we need to use the chain rule. So that's going to give us 3. And then we've got this parabolic cosine squared times the parabolic cosine prime. And then for this next bit, I need to use, let's see, well, it's the chain rule along with the fundamental theorem of calculus. So that's going to give me, in the end, something like this. We'll have plus 2 times this parabolic cosine squared minus 1 times the parabolic cosine prime. And then that needs to be equal to the number 1 because the derivative of t is equal to 1. Okay, so now what we'll do is observe that what we have here is an equation that can be easily solved for the derivative of the parabolic cosine. So let's do that. So we've got parabolic cosine prime. We can factor that out of this left-hand side. And that's going to leave me with 1 minus cos p squared t. And then plus 2 cos p squared t minus 2 equals 1. But now observe that we can take the terms here in these parentheses and most definitely combine some. And we'll end up with a minus 1 minus cos p squared t. Okay, but what does that tell us? Well, that tells us that we can have the derivative with respect to t of this parabolic cosine is negative 1 over 1 plus the parabolic cosine squared. Okay, so there we've got it. We've got the derivative of the parabolic cosine. And then, well, we can grab the derivative of the parabolic sine simply from this equation right here. And I won't do the derivation. It's just like some standard symbolic manipulation. But what we'll end up with is the derivative of the parabolic sine is 2 times the parabolic cosine over the parabolic cosine squared plus 1. Okay, so we've come up with the derivatives. Now let's see what else we can get out of this equation. Okay, so we've got those derivatives that we came up with on the last board. And then I think it's a nice exercise to take the second derivative of each, apply this formula as needed to see that you in fact get 0. Okay, so now let's start with this defining property of parabolic cosine and do something else. Let's just, integrate it, which we can do because we've got a polynomial right here instead of something a little bit more complicated. So that's generally why we have those strange definitions for the regular cosine and the regular sine in terms of those areas, because, well, they involve integrals that you can't really evaluate without those functions. But here, that's not the situation. Okay, so let's get at it. So if we integrate this term, well, what we would get? Well, the first couple of terms will be the same. So we've got parabolic cosine minus parabolic cosine cubed. And then we'll have plus 2. And then let's see, we'll have u minus 1/3 u cubed evaluated at the top and the bottom. So let's see, that's going to give me something like this in the end. So we'll have plus 2 times 2/3. So that's going to be 4/3 from the evaluation at 1. And then we'll have plus 2/3 times this parabolic cosine squared of t minus 2 times the parabolic cosine of t. So that's what we get. So just to reiterate, I definitely didn't go through all of the calculation there, but this stuff from this bit to this bit is equal to the evaluation of this integral. But now let's observe what we have here. We've got this parabolic cosine that should be cubed is satisfying a cubic equation. So let's see, cos pt is a solution to the following parabolic equation. So we'll have z cubed plus 3 times z plus 3t minus 4 equals 0. So obviously I cleared some denominators there and I put some stuff together. Okay, so notice that there is a cubic formula that you could use to solve for z in terms of t. I'm not going to do that, but you could write that down if you wanted to, and you would have some interesting expression involving cube roots and square roots for the parabolic cosine, and thus you could get one for the parabolic sine as well. What I'd like to do right now is present some formulas that come from this paper over here. So about parabolic trigonometry that relate the parabolic trig functions to hyperbolic and normal trig functions. So maybe I'll just put this as an observation. So let's see. We have, in fact, the parabolic cosine of t is equal to minus 2, the hyperbolic sine evaluated at 1/3 times the inverse hyperbolic sine evaluated at 3t minus 4 over 2. Okay, and then we also have the parabolic sine is equal to 3 minus 2 times the hyperbolic cosine of 2/3 times the inverse hyperbolic sine of 3t minus 4 over 2. Okay, so that's a cool relation between parabolic and hyperbolic trig functions. And we'll have one more between parabolic and normal trig functions. And that is the parabolic cosine is equal to 1 over 2 times the normal cosine times, well, we have the square root of 4 minus sine squared of t, and then minus sine of t. Okay, and then what about for parabolic sine? Well, we're going to have something like this. We'll have tangent of t over 2 times cosine of t, and then we actually get that multiplied by the same thing. So we'll have the square root of 4 minus sine squared t minus sine t. Oh, and I missed a 3 that should be multiplying this sine squared inside of those square roots. Okay, so there you have it, a nice exploration of the parabolic trig functions, and that's a good place to stop.